right, here we go.
So hi everyone, my name is Tyler Whitaker. I'm an applications engineer, as mentioned, with Teledyne Marine. Today we are going to be talking about the Blueview 2D imaging sonar. So let's go ahead and jump right into it. So just an overview, few notes here of kind of what we're going to be reviewing today. What is our 2D forward-looking sonar? Various image characteristics of the 2D image, how to interpret it. Teledyne Blueview sonar options. All of our sonar offerings are kind of full suite of 2D sonars. Various applications that the sonars can and are used in, of which there are many nowadays. Then we're going to jump into the ProViewer software, which is our main acquisition software. Just kind of give you some tips and advice on using that, and we're going to go over some data review as well. Then a few use case examples, have some interesting videos that go over some of our 2D data, and then just a Q&A at the end to go over any questions you guys may have. So again, feel free to write down questions as I go along here, and then we'll definitely address those at the end. They want to make a quick comment. This is not a comprehensive 2D training. This is definitely kind of an overview, but if you are interested in more, if you own a system and you are interested in more comprehensive training, feel free to contact us. We can discuss that and make sure we get what you need. So what is 2D FLS, forward-looking sonar? Teledyne Blueview's 2D sonar is forward-looking multi-beam imaging sonar. A lot of words to describe really a simple thing, which is we're producing a image much like an acoustic camera, a real-time image. So 2D forward-looking sonar is kind of a class of sonar that was traditionally used for vessel navigation and awareness, looking forward in front of the vessel. Though the uses of modern forward-looking sonar go well beyond this scope. It's not necessarily just forward-looking, it's looking in any direction, of course. Forward-looking is still a very common use of these types of sonars, but really it's whatever your imagination can dream up as far as these uses, potential applications of these sonars. They are very compact, they're low power, they can fit on any number of vessels, AUVs, ROVs, surface vessels, of course. And they are motion independent, so whether you're sitting still or underway, again, much like a camera, an acoustic camera, the image isn't going to change. You can be moving, almost full speed and still get a usable high resolution image. Jumping into kind of the image characteristics, so probably one of the more important things to look for when, I guess, shopping for a 2D sonar or looking into what 2D imaging sonar will work best for you are the horizontal field of view and the vertical field of view. So horizontal field of view obviously is the kind of the viewing angle, the wide field of view indicated here. Do this, indicated here in the yellow. And then the vertical field of view indicated in the red is the height of the viewing angle. So a good analogy here is like a spotlight kind of flashlight in a very dark pitch black room. You're only really going to be illuminating what you're pointing the spotlight at. Everything outside of that cone of light is going to be completely obscured in the dark. Same kind of thing with sonar. We have a kind of a viewing cone. Anything outside of that is going to be obviously not in our actual imagery, but everything inside that cone will be captured by the sonar. So very important to know what you're looking for, what your kind of desired outcome of your application is. That will really help you determine what the appropriate viewing angle is. An example, our M900-130 model. It's one of our 2D sonar, our very common 2D sonar models. It has a 130-degree horizontal field of view and a 12-degree vertical field of view. So that's kind of one of our more standard offerings. So this is important. This is jumping into the actual image we're going to be seeing when we actually use our 2D imaging sonar. So we have the same little drawing on the left. We have the sonar mounted to a little ROV here, just looking at these bridge footers. There's a little piece of rubble, I guess, in the center. What we're actually getting on the top side in our ProViewer software is on the right here. So we're actually getting a top-down view of the scene, of the underwater scene. So we can see the bridge footer on the left is imaged here on the left top-down plan view of our sonar, and the bridge footer on the right is seen here, just the edge of it, and then that rubble is seen in the center. So really important to kind of make the switch in your head of you're actually seeing a top-down view of the scene. You're not seeing kind of a point of view type view that you would kind of logically think you would see. You're actually seeing just a bird's eye view. So very important to kind of understand that's what you're seeing with this type of sonar. To jump further into that particular image, there's various different things going on. There's brighter pixels, there's dimmer pixels, and then there's areas of no pixels at all. So as would logically seem, the brighter pixels are actually indicate stronger returns, stronger acoustic returns. So stronger returns come from perpendicular surfaces or edges to the sonar, or hard or acoustically reflective materials. Dimmer sections, like we can see on the top of the bridge footer here and kind of over here, usually represent angled surfaces or soft or kind of acoustically absorbent materials, which makes sense, right? If we have a perpendicular surface, our acoustic signal is going to, more of our acoustic signal is going to be returned directly to the sonar. If we have an angled surface, more of it's going to be reflected away. And then dark sections, much like light, is just a shadow. It's a place where we're getting no returns at all. Usually because there's an obstruction between the sonar and that area, creating that shadow. So very much the same as you would see with light. This is interesting, talking about different types of acoustically reflective or absorbent seabed types. Don't worry too much about the details of this graph, angle of incidence. We're not too concerned about that. I did want to include this just because it gives you a good representation of what different material types, what kind of backscatter strength or really strength of return you're going to get. So makes sense, rough rock is going to be your strongest return. Going down, we have kind of smooth rock, cobble, down to different types of sand. As we're going down here, we're getting into more and more absorbent materials. So a lot of these are going to absorb more of the signal, meaning less is returning to the sonar. So we're going to have in our software really dimmer pixels between, say, a rough rock and a fine silt. Another very important concept we try to get across. A lot of people have trouble with this initially when they're brand new users for our system, is the grazing angle. So really the tilt angle of your sonar, whether you're on a surface vessel or on a subsea vessel, ROV, the tilt angle is going to be very important. If we're tilted down too much, like seen in the top image here, we're going to really just illuminate a small sliver of the seafloor. You can see that represented in your actual view. This is from our software. It's just kind of a narrow band of returns. This is, generally speaking, not what most people want. What is kind of more preferable is the bottom image, which is a much shallower grazing angle, meaning we're grazing the seafloor here. We're getting a very large area of coverage, which really fills our swath. We can see the full area of seabed here. In fact, we see an object we didn't see in the top image. So generally, this is going to be the image most people want. Of course, depends on the application, but this is all dependent on grazing angle, which kind of drives the point home of having a way to adjust the tilt angle in your deployment, whether that's through just kind of a manual hands tilt and lock mechanism on your pole or on your vehicle, or having a pan and tilt where you can actually control the tilt of the sonar through the software, which is an option we have. Because this can be very useful, especially if you're changing depths. If the seafloor is going, of course, lower or higher, you're going to need to change this tilt angle to get the ideal grazing angle. So that's where a tilt control comes in handy. But overall, just a very important concept to kind of grasp. Moving on to our offerings, of which we have quite a few. You can see them, some of them pictured here. So we have really there's a number of different configurations, but the main thing to take away is that there's really two primary characteristics, specifications. One is maximum range you need, and one is resolution, or I guess image quality, generally speaking. So if you require a max range, you're going to look at kind of a lower frequency. So we have really three frequency offerings. We have a 450 kilohertz, 900 kilohertz, and a 2250 kilohertz models or heads. So 450 kilohertz, our long range is going to be 300 meters max range. But of course, with that trade-off, you're going to have the lowest resolution of three. Moving up from that, you have a 900 kilohertz, which is kind of our mid-range model, good balance of range and resolution. Definitely our most common head by far. And then moving up step, you have the 2250 kilohertz, which is very high frequency and very short range. So 10-meter range, but with that high resolution. In fact, we only sell this head as a dual head with the 900 kilohertz. So those are actually these two models seen here, which allows you to kind of benefit from the versatility of having the 900 kilohertz head, good balance of range and resolution. And when you have an object that you really want to get higher detail on, you can click a button and switch over to the 2250 kilohertz, get a very high resolution image. And we have a video just in a bit kind of demonstrating that. Depth ratings are 1,000 meters and 6,000 meters. Those are our two main offerings. 6,000 meter up at the top here. These are titanium electronics cans. And really at the end of the day, we like to talk to our customers about, okay, what is your application? What is your desired outcome? And really based on that, we can make recommendations on what type of sonar we think will benefit you the most. So we really like to discuss potential applications or uses, and then kind of jump into all the different configurations. So, configurations suited to any number of applications here. Do want to briefly touch on the Blueview M Series Mark II. So M Series, generally speaking, is the name of our 2D imaging line. The Blueview M Series. The Mark II is our kind of our latest and greatest iteration of this product. So we recently made a number of upgrades to the product. I'm not going to read through this entire slide. There's a lot of words, but the main takeaways are we have improved the data quality over the entire field of view and range. We've also dramatically improved the reliability and kind of the ruggedization of the transducers specifically, which are at the front here. These are, of course, the components that both emit and receive the acoustic signal. These are can be fragile components. Over time, they can wear down. The lamination on them can break down. We've really improved this to extend the lifespan of the sonar and just the overall usability. So on that note, we do have a quick little minute clip of a video. One of my colleagues, who's actually the Blueview product line manager, gave a demo not too long ago on the Blueview Mark II product. And later in the demo, he actually compares the 900 kilohertz and the 2250 kilohertz head. Again, he's using a dual head sonar. He's going to click over between the two heads and show you kind of the difference between the two frequencies and what you can expect. So let me jump to that point in the video. Okay, I'll go ahead and click play and let him take over.
900 kilohertz. You can actually compare here with the 900 kilohertz that you can see structure, you can see the vertical areas, but the resolution is just not nearly as good as the 2 megahertz. So this really shows the strength of the 2 megahertz here. I'm going to show now, I'm just going to stop recording here, but if I take this 900 kilohertz data where it's pretty blurry and where the resolution, although one could say is good, it's not phenomenal. If you go over to the 2 megahertz, one can see, once I just get it back into context view here, the resolution is far superior and the structures are far clearer to see. You can see the boulders and the boulder detail here as well. So that's really, really fantastic, actually. So here
I'll pause in there. This video is actually available online on our website. There's kind of a video section, so it's about a 25-minute demo. If you are interested in the Mark II or just in the M series 2D imaging sonar in general, highly recommend going on there and watching that. I believe we can link to it after this. Jumping into applications, there are a number of applications. This is a very small list compared to what what we've seen over the years with these imaging sonars. I do want to go over just a couple examples for some of these categories. Navigation and charting is obvious. That's historically the most common use. Forward-looking sonar, using it for navigation, obviously makes sense, pretty straightforward. Construction is becoming very common nowadays, construction and inspection. Things like pre and post construction verification for bridges or dams or any offshore or even inshore kind of structure, marine structure, doing pre and post verification of that construction with the 2D sonar provides a really good visual kind of check on a build. Similarly with inspection, we have pre and post like salvage verification, inspection of infrastructure like bridge footers for scouring, for any other type of damage. You know, that's become kind of a big topic, especially with bridges on high flow rivers, looking at these footers for damage, trying to prevent any potential catastrophic collapse or anything like that. So using permanently deployed sonar or even doing just monthly surveys with the 2D sonar is a very quick way to verify kind of the integrity of these structures. Search and recovery makes sense. It's a very wide field of view sonar. It can go up to 300-meter range on our 450 kilohertz model. Large area searching while still maintaining that high resolution to identify even smaller objects. Obstacle avoidance, again, makes sense. AUVs, autonomous surface vehicles or underwater vehicles, forward-looking sonar has traditionally been the best option for that, specifically the Blueview systems. Marine wildlife management is also one that's becoming a bit more common. Stuff like population migration study for fish, marine mammals, a lot of stuff up here in the Pacific Northwest that a lot of people have been using it for that kind of thing. Really, there's endless amounts of applications. You know, one of the most interesting parts of my job is seeing what our customers come up with, where they stick these sonars and what they kind of dream up and different ways to use these. So example of that is a recent kind of university project where they're using the sonar to give basically an autonomous underwater robot vision, using computer vision and AI to basically take the sonar data, interpret the data, and kind of identify the object, and that will dictate how the robot then interacts with the object. So kind of very advanced stuff that much of it's well over my head, but still very interesting nonetheless. Platforms, because it is a compact system, it's low power, you can really stick it on any number of platforms. We do have work class ROVs, been a historically common use offshore, sticking them anywhere on the ROV just to look at offshore oil rigs or any offshore structure. This is becoming very common. It has been common historically, but is becoming more of kind of a popular application, sticking it on your small ROV. We actually have our Teledyne Blueview ROV on the right here. It's commonly sold with the Blueview 2D sonar. You can imagine the uses of that for navigation of the ROV, for quick inspections, places where you can't get a surface vessel. Speaking of surface vessel, boat mount system, very common, probably the most straightforward. Attaching the sonar to a pole, hanging it over the side will get you some really incredible imagery of whatever you happen to be looking at. We actually have a product called the BV3100, which is essentially just a pole with a pan and tilt on the end, and it has a clamping system that you can attach to your surface vessel. Really is kind of a turnkey way to attach this to a surface vessel. And then, you know, diver handhelds, very common, tripod mounted systems, permanent deployments. Really anywhere you need underwater vision, you can attach this sonar. There's a lot of flexibility with the system. So a couple of use cases here I want to go over. They're kind of short videos. This first one is just a quick inspection of a 40-foot deep ship terminal. It's just a 900 kilohertz head examining the ship terminal. At some points in the video, you can see some kind of dredging scars on the seafloor. You can also see some tires, which are common everywhere. You always get tire imagery. So let me go ahead and play this and okay. So we can actually see the key wall here on the left. Again, we're top-down view. This is the sea floor. You can see the dredging scars along the bottom there. You could even tilt the sonar up a bit. Looks like they just did, to increase that grazing angle. So a good example of grazing angle here, and how you can really expand your coverage just by tilting up a few degrees. And then there are some tires here, I promise. There's one, see here, and then a few more there. Great. So pretty straightforward use of the 900 kilohertz system. Another 900 kilohertz system here. This is just looking for a buried cable. So let's play this, have a few comments. Oops, sorry. So the first thing I want to point out actually is here on the right, you know, because it is a 2D system, we're only getting 2 dimensions, of course, so we don't really get that Z, that height dimension. So here we actually see these shadows. You can generally use shadows as a good indicator of object height. You know, not always, but a lot of times you can see if it's a much longer shadow like this, you can generally guess that this object, let me get my pointer back up. This object right here is going to be quite tall because it does have a very long shadow. So because of kind of the cluster here, you can generally guess that this would be a dock. These are just wooden dock pilings likely. So things like using the shadows and using various features in the imagery really allow you to analyze the imagery better real time, and using shadows to your advantage is a good way to do that. Let's continue. You can also see some sand waves here on the left. And then the buried cable on the left there. Or I guess free spanning cable. Again, you can see the shadow of the cable there. Okay. And then one more example, and then I want to jump into the software quickly just to give a brief overview. This is just on a small ROV. This is just an ROV culvert inspection. I'm just driving through. I'm not sure if they were searching for something or just a general inspection, but you can see in comparison to the ROV video, which is very low vis conditions, pretty common in most waterways. You can kind of see the image the sonar is actually giving you. This is the 2250 head, the high frequency head we're seeing right now. Great. Okay, so quickly, I want to just jump into the software. our ProViewer software is what it's called. Okay, so this is our main ProViewer software. This is our acquisition, our recording software for the 2D system. Just want to open up a quick data set here. This is a data set of just a bridge inspection. We actually have a bridge footer here. You'll see a number of sandbags, kind of a concrete mattress around the footer. But the main point here is I want to go over some of the basic features and functionalities of the software. On the left here, we have a range slider, which will allow you to adjust the max range. We do have kind of the sonar model, serial number, various things like that in the top right. In the lower right, we have other details, the date, the ping number, ping rate. And because we're playing back data, we of course have a kind of a playback controls at the bottom here, which you wouldn't have connected to a live sonar. So probably the main feature of ProViewer to be aware of is what I call the right-click menu. So named such that if you right-click anywhere on the wedge, you'll get this little menu. First item here is sound speed. Sound speed is important for sonars. Not as much for a 2D imaging sonar as say like a bathymetric multibeam sonar, where it's very critical for accurate data. For 2D sonar, it's more important just to get a more seamless image, but not nearly as important as a bathymetric sonar. So if you have a temperature recording of the water, you can calculate it. If you have a sound velocity sensor, you can use that and just slide this depending on what you actually have. But this would be the place to adjust that. Color map, this is based on preference, just changes kind of how the data is represented. Most people use the default copper just because that's what the default is. There is a jet option, which is kind of a heat map. The higher intensity returns are going to be kind of on the red end of the color spectrum. Dimmer is going to be, weaker returns are going to be on the blue end of the spectrum. Can be useful for some applications. We do have this auto intensity feature, which is on by default, and I typically recommend leaving it on. It's basically the software making adjustments on your pixels on what you're viewing to make it appear to what the software thinks is as clear as possible. So if you aren't getting a clear image, if your image is blown out or it's too dim and your auto intensity is checked, it means the software is not, it's confused by something. So that's why we allow you to disable it and basically adjust various different properties of the image manually. So there's descriptions of all these properties in the manual, but I'd say for a good 75% of applications, auto intensity will do a great job. Couple tools up here. We have a measurement tool. You can draw a line and make a measurement. Of course, zoom tool. You can zoom in or out. Rotate, and probably most importantly, we have a screenshot tool, a video tool. You can create subsets of the data to kind of trim the data into smaller pieces. So this is what a lot of people want for their deliverable at the end of the day. Is screenshots, videos, things they can email or put into presentations. Settings here, I'm not going to go deep into these because, again, this is kind of an overview, already going over time here, but number of different settings. We try to keep the software simple, but we do have this advanced settings option that will give you a lot of powerful tools that you might not otherwise think of just by default, but we do allow a lot of flexibility with these advanced options. And most important probably is the help tab and the open user manual tab. So this will bring up the user manual, which will give you more details on all of the functionalities in ProViewer. So that's kind of just a very brief ProViewer interview. So I'm going to jump back into the presentation here. Okay, so back, one more thing with the ProViewer software. There is a Sonar settings tab. I have it pictured here because I wasn't connected to a live sonar, so the sonar settings didn't come up. But you can see it allows you to set the IP address of your sonar. It allows you to change a couple of hardware settings, gain, time variable gain, source level, which is the amount of energy you're putting into the water. So these are all pretty important settings. Again, if you're not getting the image you expect, maybe you're in a very small area, you can dial down the source level to get kind of better image, because you might be putting, for example, too much energy in the water. We actually have controls to allow you to change some of these hardware settings. So let's move on. There's one more thing I want to kind of go over before we get to Q&A here. It's just a nice little, I guess, added feature of the sonar, in that our general view is the horizontal field of view is kind of our long field of view, is giving us this top-down image. If we turn the sonar, if we rotate it 90 degrees, we actually get a side-in kind of profile view seen here. So this is a barge. We can see our normal top-down view of the barge. If we were to rotate the sonar 90 degrees, we get this side profile view. We can actually see the seafloor. We can see the height of the barge. And this is all we did was just rotate the sonar 90 degrees. You can see the red vertical swath is going to give us this profile image. So a very good thing for particular infrastructure inspection. We have, attached it to a surface vessel, drove across these bridge footers, got this really incredible imagery. Of course, we just mosaicked it, photoshopped it to an actual photo of the bridge, but really useful for looking at the condition of kind of taller structures. Not at all useful for navigation or just general use. That's where the more common horizontal orientation comes into play. But if you know what you want to capture, like on a bridge footer, turning that sonar 90 degrees and just driving along the bridge footer will really get you some incredible imagery. And have just a quick last video here demonstrating that. This is, as you can see, driving alongside a brick wall here in the vertical orientation. And we can see the seafloor on the bottom here, and we can see the kind of the details on the brick here in the video as we drive along. All right, and that's the end of that one. Okay, so that's all I have for now. Like I said, we have plenty of data examples. If you have a certain application in mind, you can contact me directly. Here's my email and my phone number. I can send you any amount of data or videos that kind of more pertain to what you're looking for. And yeah, we'd be happy to talk further. But yeah, for now, if anyone has any questions, feel free to go ahead. Okay, thanks everyone. This is
Hey Tyler, I'm okay. It's all good.
You're here? Okay.
Yeah.
Kind of thought I would come back when the video ended. Part of me did.
Yeah, that was all part of the fun. Yeah.
Yeah, right.
Yeah, for everyone on the back end, there was a lot of text exchanges going on. I'm like, oh my God, my computer's locked up. Oh.
Yeah.
All right, great. Let me go back to sharing here. So yeah, we're on the learning curve here, figuring this out. Okay. All right, and we do have some questions, which is great. So again, everyone, if you have any thoughts, any questions, please type them in, and we'll start running through these. And also, if you have additional training topics that you'd like to hear, we are wanting to put together a Blueview training series, and I think it's just a product that's well suited for these types of sort of quick sessions with some Q&A at the end, and we can pick some key topics. So if you want to just type that in on questions as well, if you have any suggestions, that would be great. Also, I want to give a quick shout out because I see Stockton Rush and Michaela are both on from Ocean Gate, which is that gorgeous image in the background there of that vehicle. So very cool organization. They love their Blueviews. They use them to get some amazing data. Yeah, some really cool stuff. So thank you for joining us today, you guys. Okay, first question, is Blueview a true multi-beam system with individual transmit receive elements?
It is, I guess, technically, I guess, depends on your definition of true multi-beam, but there aren't separate transmit and receive elements. They're actually built into one, just what we call just our transducer that does both transmit and receive. So it's multi-beam in the sense that there are 768 beams in like our 130-degree field of view. It is multi-beam in that sense. I guess we try to differentiate between what people think of as traditionally as multi-beam, which is kind of bathymetric, downward-looking sonar, which is traditional bathymetric sonar. Of course, this is forward-looking multi-beam sonar, so the transducers function in a little different way, but there is a difference between us and some of our competitors is the fact that there aren't separate transmit and receive elements that are actually built into one transducer. So yeah, hopefully that answers your question.
Okay, great. Yeah, and Trevor, if you need any additional information, just reach out to us directly if you're looking for more.
Absolutely. My email, hopefully jot it out. Otherwise, we can send it out. Want to precursor and just say if you do have any questions at all, kind of follow up to this, feel free to reach out to me. Data examples, anything else.
Yeah, and we'll be sure to include that in the e-blast that you're going to get tomorrow with the link to the recorded webinar, so you can reach out to Tyler directly. Next question: can Blueview be used for inspecting small details, for example, damage to a ship hull?
Yeah, absolutely. In fact, that's probably one of its strong suits is doing kind of visual inspections of structures, of ship hulls. Really anything you want to get kind of a acoustic camera visual look at. For a ship hull in particular, the deployment can be somewhat more difficult depending on the size of the ship, depending on a number of different things. We have had users use kind of ROV crawlers that can essentially suction to the underside of a vessel, mount the Blueview kind of center of the ROV and just tilt it. If you remember the grazing angle, tilt it so the grazing angle is just grazing the ship, and basically just kind of comb the hull of the ship with the vehicle to get a really high detail kind of image of the ship hull, particularly with the 2250 kilohertz head, which has that very high resolution. So if you don't have an ROV, there can be a number of other ways, using just another smaller surface vessel, moving around the ship with a pull mount over the side, just slowly or at full stop alongside the ship, using either a pan and tilt or a manual tilt to kind of adjust to point the sonar at the ship hull. Again, making sure to get a grazing angle that really is giving you the most coverage on the ship hull possible. But yeah, it's very, very common use for just general inspection, and certainly for surface vessels as well as subsea structures. There's just a few details in the deployment that need to be kind of considered.
Okay, great. And kind of going back to OceanGate, they're going to be using the Blueview for exactly that purpose. They're going to be actually diving on the Titanic this summer. So we're really looking forward to seeing some of that data.
Yeah, there's a ship hull inspection.
Yeah, right? The mother of all ship hull inspections.
Right.
So can these sonars be used with pan and tilt system to collect 3D data?
That's a good question, and it's one we get somewhat often. And the answer theoretically is yes, they can be. The reason they aren't really well suited for that comes into how the beams, basically the beam angle. So if you look on our website, or it was in the presentation, we have that horizontal viewing angle and we have the vertical viewing angle. Vertical viewing angle is generally around 12 degrees on our 2D systems. If we were to flip that in the 90-degree orientation, like we saw at the end of the presentation, that would be how we'd scan on a pan and tilt, like we do with our 3D BV5000 product, another product we have. The thing is that angle is 12 degrees, which is quite a wide angle. Gives you a lot of uncertainty in your soundings and your 3D points when you're scanning across the environment. Our actual 3D product is, for all intents and purposes, the same as the 2D, except instead of 12 degrees, we squish that down to 1 degree. So we have a 1 degree by 40 degree beam swath on the 3D product, and that 1 degree kind of very narrow, very thin swath is scanned around the environment to generate a high resolution 3D point cloud. You could do, again, you could do the same thing with the 2D, but you have a 12-degree field of view instead of a 1 degree. So you have a lot of uncertainty in your points. You're going to get a 3D image, but it's going to be very inaccurate and really low resolution as compared to our 3D product. Another thing is our current software doesn't support that. So we don't have kind of turnkey software to create a 3D image from a 2D sonar. So any generation of a 3D image would need to be done with our SDK, which is our software development kit, which gives you the tools to actually develop your own software with the sonar. Or you would have to use something like Teledyne PDS or HiPack or a survey software package to do that. So yes, you can. No, we generally don't recommend it, but it can be done if you have a very specific application where you don't require high resolution. You can definitely make that happen with our 2D sonar on a pen and tilt and special software.
Okay, great. And if you'd like any more information on that, again, reach out to Tyler. I know that's a fairly complicated.
There's a lot to that subject. So
yeah, it's a good deep question for sure. So yeah, feel free to reach out to Tyler if you'd like any more on that. But and also we have all kinds of great 3D systems, right, Tyler? So there's
we do. I mean, we have a whole suite of products for 3D specifically. So.
Absolutely. Okay, another question. Has there been an optimal angle determined for the ROV on a relatively flat seafloor surface to reference as a starting point?
Yeah, so I guess talking about grazing angle, if you have a completely flat surface, I mean, it depends on how wide of an area of coverage you want. I guess generally speaking, anywhere from, we'll say, maybe 10 to 20 degrees off parallel with the seafloor would be good for a grazing angle. It really all depends on your depth, right? So if your ROV is closer to the bottom, you're going to need a much shallower grazing angle. Your sonar is going to need to be much shallower. If you're much higher up, you're going to need to tilt the sonar down. So it really is kind of a dynamic thing, which can be difficult with an ROV, especially if you don't have kind of a tilt mechanism on the ROV, as most people don't. On an ROV, it's difficult to control the grazing angle with a high degree of certainty, just because you're piloting the ROV, and the ROV can kind of pitch up and down quite a bit. So really on an ROV, it's just used truly as kind of an acoustic camera, and that it's on there, and if you're thrusting forward, you're going to get maybe the ideal angle, and if you're actually holding station, you might actually be completely flat and just be looking ahead and just slightly grazing the bottom. So a little more difficult to control that angle in ROV, but it really isn't too impactful in most applications because it is a large field of view. So if you have it on the front of the ROV, you're going to get a good image of what's in front of you kind of regardless. And it's not really worth it trying to stress out about the exact grazing angle at any given time on an ROV. But generally, if you had exact control over the tilt angle, depending on depth, if you're quite close to the seafloor, a nice shallow 10 to 20 degree angle would work well, with that angle becoming larger, steeper as the depth decreases.
Okay, great. Got another one for you. How was the underwater image of the two bridge piers created? Was that image a snapshot?
Yeah, that's a good question. So the two bridge piers was actually done by a colleague of mine. So again, sonar was flipped vertically. It was off the side of a surface vessel. I think this was all explained. And what we do in those vertical shots is if you can picture a surface vessel, pull mount off the side, and then we have it in a vertical orientation, and we basically pan it or hand rotate it to kind of just point at the bridge footer. Again, talking about grazing angle, we want to graze the side of the vertical bridge as we drive by on the vessel. So we did that, and we also used basically some mosaicing software, I believe in that case, to stitch together these 2D images. to make kind of one large 2D image. It was either stitching together or it was just one static sonar shot, but it was actual sonar data that was taken. It was just kind of screenshotted and then brought into Photoshop to stitch it to a topside photo. So nothing fancy or nothing in our software that allows you to real-time stitch kind of a photo to sonar data, unfortunately, but it's quite easily done in just Photoshop or even MS Paint or something basic like that. But yeah, I think it was just a static shot of the sonar and just brought into Photoshop and attached to a photo. We actually do that a lot for a lot of our marketing material. It does obviously create a pretty striking image, which really gives you some context for the sonar image to actually see a real life photo of the above water.
Yeah, it's pretty cool. It tells a story for sure when you're looking at it. And some of the tunnel images that you guys have, those are really amazing too.
Oh yeah, there's all kinds of good data out there.
Yeah, it's crazy. All right, any more questions from anyone or topic suggestions? Like I said, for the training series that we're going to start, it sounds like there are quite a few questions just surrounding mounting on a vehicle. So Tyler, that might even be an interesting one that you could get a little more in the weeds on that one.
Oh yeah, yep.
So, all right, well, we appreciate you guys giving us almost a full hour here today and for being our guinea pigs on this first version of us trying to record it in live with some video cameras on. I think everyone's just getting really tired of looking at PowerPoint. So we're trying to change it up a little bit, make things a little more dynamic and interesting. And so to that point too, if you've got any suggestions on what we can do to make anything more engaging, let us know as well. So, because it looks like we're going to be with you guys for a while online before we're back in person. So yeah, let's make it work. So. All right, Tyler, thank you. Super informative. You are a fountain of information, as always.
You're very welcome. Thanks everyone for coming out and listening to me talk for a while. But yeah, feel free to email me if you do have any questions, data requests, anything like that. I'm wide open.
That's great, thanks. And that is, we want to be here for you guys. That's why we're here. It's not just selling a product. We want to make sure that you're using them and optimizing after you've got them in hand. So, don't be shy, reach out to us. We're here, we'll get back to you and get you guys sorted. So everyone have a fantastic day and we hope to see you online again soon. Take care, everyone.
Thanks.